We have learned how to convert the rectangular coordinates into polar coordinates. As in the parametric equation, we can ask the similar question. Can we do the similar things in polar coordinates as we did right in parametric equations or in rectangular coordinates? One of the problems we are going to deal with, okay, with polar coordinates are the area problems. To figure out an area, let's look at an example, okay, how we can calculate an area using the polar coordinates. So let's say I have an area, something like that. Look at that. So, and I can represent this area, look at that, by this curve. This curve, of course, should be given by polar coordinates. And then, as you know, right, I need to give my function in our theta pairs. And then this is going to be one of my, right, the alpha, the theta value, and the other one, right, from here to there, right, there is another theta value. So to calculate this type of area, first we need to remember, okay, how we can calculate a sector, right, in circles. Remember, right, to calculate such a sector in circle, first of all, we need to calculate the circle area, and then we need to take the percentage of, right, the sector. The percentage of the sector, of course, is going to be equal to theta over 2 pi. So pi will go away, and the sector area then would be equal, right, 1 over 2 r squared theta. If I apply this same approach to, okay, look at that, this area, I can, right, take a small sector here, you see that? Small sector, and then I know that I can figure out, right, this small sector area using the same formula. And I can continue, okay, doing this one between the alpha and then beta. So, but as you see, right, to calculate the whole area, right, I need to use, right, the infinite millisector. That's why, right, I need to use an integral, as you all remember from, right, the Riemann sum. The area problem will turn into the, look at that, this formula. Alpha to the beta, 1 over 2, right, the r squared, the theta problem. So r is here, look at that, my function. That is why when you figure out, right, the area in polar coordinates, that's going to be the formula I need to use. F of theta squared d theta. So let's look at some examples, right? Example 1, if my formula is correct, it should be working for simple circle problem. So I want to find out, right, find the area inside the circle. This circle is something like that, as you know, right? This is my circle. So my radius is 2. So I want to figure out, right, this area. How am I going to find out? The area is going to be equal from 0, right? My angle is going to be 0 to the 2 pi. Now 1 over 2 times, right? What is r here? R is equal to 2 squared d theta. So if I take the integral is going to be equal to theta, 0 to the 2 pi. So the area is going to be 4 pi, which is equal to, right, the circle area. Okay, another example. Please figure out, right, the area inside this cardioid. As you know, right, when you are given, right, such a formula, this is one of the cardioid formula, and it was something like that. Since if I have the, right, the plus here, the cardioid, bigger side of the cardioid should be on here, right? And then the small part of the cardioid should be on the left-hand side of the x-axis. So I want to figure out the area inside this cardioid. It is 1, 1, 2. Okay, so area will be equal 0 to the 2 pi, right? 1 over 2 times r squared. What is r? R is equal 1 plus cosine theta squared d theta. Okay. Do you remember how to take the integral of this function? From the, right, this trigonometric substitution, if you remember, right, 0 to the 2 pi, 1 over 2, 1 plus 2 cosine theta plus cosine squared theta d theta. And 1 over 2, I can take this out, 0 to the 2 pi, 1 plus 2 cosine theta, but instead of cosine squared theta, I need to use, right, one of the identity I use, 1 plus cosine 2 theta over 2 d theta. Okay, the integral of 1 is going to be equal theta plus the integral of 2 cosine theta is going to be equal to sine theta plus, right, the theta over 2 and sine 2 theta over 4. My bounds are going to be 0 to the 2 pi. Let me use my bounds. 1 over 2, 2 pi, 2 sine 2 pi, which is 0, right? Theta over 2, theta was equal to pi, which is pi, and again 0. Good. So now I have the 2 pi plus pi, and now for the 0, right, I will have 1 over 2, theta which is 0, sine theta which is 0, everything is going to be 0, right? So the area is going to be equal 3 pi over 2. Now, I want to look at a little bit different problems, like the area between the curves we solved before, right? So can we do the similar things, right, in polar coordination? Look at another example. Find the area inside r is equal to sine theta and outside of r is equal 1. So to do that, right, let me see, okay, what area I need to figure out. First, I'm gonna draw, okay, these two circles. The second circle is, right, the normal circle. Look at that. It is just a regular circle. The radius is just 1, and at the center. So, but the first circle is the circle, right? It should be on the y-axis. Okay, this is the circle. So, the inside, the 2 sine theta, but the outside of the, right, second circle, that should be, right, this area. As you see, to calculate this area, I need to, right, subtract the area on the, right, the first circle, and I need to subtract, right, this area. Look at that, area 1, and then if I look at here, area 2 minus area 1 is going to be equal to my area I want to figure out. To do that, first of all, I need to find out, right, these 2 points, theta 1 and then theta 2, since they determine, right, my area. That's why the area problem would turn into the, right, this problem. Theta 1 to the theta 2, 1 over 2, right? Like in the, right, the curve, area between curves, this time I'm gonna subtract, right, the second area from the first area. Okay, something like that. So R2 is in this example, right, is the curve above. The R1 is, right, the lower curve. That's how I'm gonna calculate, okay, these type of problems. So what the problem, right, is to figure out what these intersection points. To figure out intersection points, look at it, I'm gonna make them equal. So where are these, right, the curves are equal each other. So sine theta should be equal 1 over 2. When the sine theta is equal 1 over 2, either theta 1 is equal, right, the pi over 6, or theta 2, which is in the second region, 5 pi over 6. So that's why pi over 6 to 5 pi over 6, 1 over 2, and R2 is equal to sine squared theta minus 1 d theta. And then I will leave the integral to you, so you can solve as we did okay before, and then you can figure out the result. One last problem I want to share with you today is this one. Find the area inside the cardioid r is equal to plus 2 sine theta, and outside of r is equal to. So to figure out, okay, the area problems here, okay, you always need to draw the shapes, guys. R is equal to here, look at that, this is the normal circle, right? Something like that. And then r is equal to plus 2 sine theta is going to be this one. Okay? So when the theta is equal, pi over 2, it is going to be 2. And this is 2, okay? So this is 4. So this is the area I want to calculate, right? To do that, as we did right before, I need to find intersection point, theta 1 and then theta 2 here. So you can just predict, but still we can figure out, right, what they are. R1 should be equal to R2 at those intersection points. 2 is equal to plus 2 sine theta. 2 will go away, so 2 sine theta will be equal 0. So when the sine theta is equal 0, right? 0, either theta should be equal, right? Either theta 1 should be equal 0 or theta 1 should be equal pi. That is why, right, I need to calculate the area between, right, these two angle area. Now what I'm going to do, I'm going to write the subtract, right, the below curve, which is R2 in this case, and then R1. R2 curve is equal to square, right? And then R1 curve is equal to plus 2 sine theta square 1 over 2, right? That's my formula from the polar coordinates area problems, and then d theta. I hope you will figure out the integrals. Okay, I'm going to leave it to you. You should apply the right trigonometric substitution to take care of this integral. So that's all we need to know, okay, about the polar coordinates area problem, and then how you calculate it. First of all, you need to figure out, look at that, the intersection points, right? Just making two functions equal each other. Then you need to figure out, okay, the area problems using the formula, like we did, okay, area in between curves. Okay, you need to subtract the curves from each other, depending on, okay, what type of shape you have. First, you need to draw it, and then you need to see who is below and then who is above, okay, and then you need to subtract them, and then just the rest is just going to be the calculating the integral, and then you need to apply, okay, some integration techniques to figure out that integral.